Hey, what's going on, guys? Mass here with another video for you. And today we're going to be talking about reverse engineering, and specifically buffer overflows. So I have some C code here, and it's pretty simple. I have a function foo here, creating like a buffer right here of about 600 bytes. We're going through prompting the user for some sort of string, and then we're going to read in about 1,000 bytes into that buffer, so we can enter upwards of 1,000 bytes here. So obviously there is a vulnerability right here. We can see that we can totally overflow this buffer. So let's go ahead and jump on in and see what we can do with that. Alright, so first things first, we need to set up our environment properly so that we can actually cause one of these buffer overflows and control the stack. And to do that, we need to run a few commands here. Modern operating systems protect against this through the use of like canaries, random addressing, and a few other things. So we're going to disable that right now. So first thing you need to do is go ahead and run echo 0, and we're going to put that into our proc sys kernel randomize va space. So that's going to turn off our random addressing here, ASLR. Next, we need to compile this program, this vulnerable C code that I showed you. We need to compile that in a specific way so that we turn off those stack canaries and we make the stack executable. So to do that, I'm going to run gcc -fno stack protector, and that is to turn off canaries, and then tac z execute stack, and that is to make the stack executable. And then following that, we're just going to type in our program, and we're going to output that to easy bof. And so now our program is compiled, and so we can see right here we have the compiled program as root. And so the next thing we're going to do is start fuzzing this program to see if it is indeed vulnerable, and to get the proper addressing so that we can control the instruction pointer, which is our main goal. Alright, so the next step here is we're going to start fuzzing this program. And so to do that, I'm just going to go ahead and create a file here. I'm going to go python tac-c, and I'm going to print 1,000 A's here. Oops. 1,000 A's here. I'm going to put that into a file called fuzz.in. So next thing I'm going to do is fire up GDB, and this is our debugger program. Basically, you're going to need to use GDB or some variant of this to identify memory addresses and just to see what's going on in the stack. So to fire up GDB, I'm just going to go GDB, and I'm going to run the executable file that we created, easybof, and GDB fires up. And so you can see here, I'm actually running GDB PETA. So PETA is like an extension for GDB. It just makes GDB a lot nicer. And if you look at like normal GDB versus this, you'll definitely see why immediately. So to run the program in GDB here, all I'm going to do is type R, and I'm going to put in that fuzz.in file that we created. And so we can see here we do get a seg fault, so basically we overflowed our program properly. And we can look down here and see that we have our base pointer, our stack pointer, and our instruction pointer here. These are the main things we want to focus on today. If we look down here further, we see our stack, and we can see that we did indeed fill up the stack with a ton of A's here, those 1,000 A's that we wrote to that file. So our next goal is to identify exactly where this instruction pointer is. And to do that, we're going to have to calculate the offset for this base pointer. You can even do it with the stack pointer, but we're just going to do it with the base pointer. And so to do that, we're going to have to create a different string that isn't just pure A's. We have to create a pattern here. So to do that in GDB, we're just going to go ahead and run pattern create. We're going to do 1,000 characters, and we're going to put this into fuzz_rbp.n. So we can see we are writing a pattern of 1,000 characters to that file there. And now we can run this again, fuzz underscore rbp.in, and we can examine the results here. So again, we got a seg fault, and you can see our stack now. Instead of just a bunch of A's, it's this pattern that we created. And if we come up to the top here, we can now look again at our base pointer, our stack pointer, and our instruction pointer. And so we see this crazy pattern that we had here. So next step that we want to do is to find that offset for the base pointer. So we're going to type $, $RBP, and this is going to give us the address of RBP. We could have also just scrolled up here and examined RBP to get the same thing, but either way, it doesn't matter. So we're going to copy this, and then we're going to type pattern offset, and you're going to give it that memory address, and we'll see we have a memory address of 608 here. So that offset is what we're going to use to access our instruction pointer. Alright, so the next thing we're going to do here is we want to see if we can control that RIP, the instruction pointer. That's our main goal behind this whole thing. If we can get in control of the instruction pointer, we can point it anywhere we want, and we can make this program do anything we want. So to do that, I'm going to head over to my other window here, and I'm going to go ahead and create a new file, and I'm going to call this exploit.py. And in here, I'm going to import struct. So I'm going to import everything from struct, and then I'm going to set my offset. And if you notice here, I wrote 616, not 608. And you're probably thinking, wait, where's that other extra 8 coming from? So if we look back at GDB here, we can see at the top here, we got the offset for our base pointer. And in a 64-bit architecture, we need to add 8 to each one of these pointers. So RSP is located at 616, and so if we started writing at 608, we would overwrite RSP instead of RIP. So we need to add 8 to RBP. So 608 plus 8 is 16, and now we can write to RIP here. So we get our offset, and then we're going to create our payload, and we're going to set that equal to A, and we're going to multiply that by the offset here, and then we're going to add to it a memory address here. And so my memory address is going to be, for now, I'm just going to write a bunch of B's. So 42 6 times 2, 3, 4, 5, and 6. So now I should overflow exactly up to my instruction pointer and overwrite that instruction pointer with the value that we set here, RIP, which is just a bunch of B's. And so we're just going to print that payload out, and we're going to get out of here, save that file, and then we're going to run that exploit, and we're going to pipe that into a new file called fuzz underscore RIP.in. Alright, so now that we have our fuzzer for the instruction pointer, let's head back over to GDB, and in here we are going to go ahead and run that fuzz underscore RIP. And if we examine the results, we can see we gained control of the instruction pointer here. It has the memory address that we told it to have, 42 a bunch of times. So now that we control the instruction pointer, our next step is going to be to point that somewhere that we want. And in this situation, what we're going to do is we're going to overwrite the stack with some shell code that is going to create a reverse TCP shell for us. We're going to connect to that with Metasploit's multi-handler, and we're going to open up a reverse shell. So first things first, we need to create that shell code. So we're going to go ahead and head over to our other window here, and we're going to run msfvenom. msfvenom is a product of Metasploit's, and it's basically used to generate shell code. So I'm going to go msfvenom, TACP for the payload, and we're going to give it a Linux 64-bit architecture, and there's going to be a shell reverse TCP, and then we're going to identify the listener host, which is us, and we're just going to use our local host, and L port, just leave it at 4444. And then we'll set our bad characters, and the reason we're doing this is because in our exploitable code, if we look here, we're reading in this 1000 bytes into this buffer, and if we read in a null byte, which is, as you'll see here, 00, it'll just end what it's reading. So it's going to cause some errors in our program, so we don't want that in our shellcode. We're going to specify a format, and we're going to give it Python. So that will begin generating the shellcode. Once we get that, we'll put that into our script that we're creating, and we'll move from there. So you can see here, we created our shellcode right here, and we see that the payload size is about 119 bytes. Alright, so now that we have our shellcode, let's go ahead and grab this. And we're going to head over to VS Code. We're going to open up that Python script that we were writing, and we're going to paste this in here. So the first thing we need to do is create what's called a NOP sled. So a NOP sled, or a no-op, is a no operation, and all that means is that if we hit this no-op or NOP sled in the memory, we're basically gonna just keep moving past it until we hit some actual executable code. So to make it make a little bit more sense, if you watch here, our payload we're gonna set to our NOP, and then on top of that we're gonna put our buff. So in memory it'll hit the NOP sleds first. If we supply it that address in the instruction pointer, it's gonna slide down that NOP, hit our buffer here, execute the shellcode, and it's going to redirect at the instruction pointer that we want. So the issue here though is, if you remember, our buff is only 191 bytes and our NOP is 300 bytes here that we created, and it could be anything. It doesn't really matter what you put this, as long as it's less than our offset value. But if you notice, it's still not going to be able to overwrite that instruction pointer because we're not reaching that 616 value. So to overcome that, we're going to create some padding here. So we'll have our NOP, our buffer, our padding, and then the instruction pointer address that we want. So let's create our padding here. So padding is going to be equal to a bunch of A's, and we're going to go offset. We're going to subtract the length of our NOPs and the length of our buff. And so now we'll create that extra padding so that we reach that 616 value right here, and then we can overwrite that instruction pointer properly. Alright, so before we can run this though, we need to set up a proper address, because if you remember, these are just a bunch of B's here. So to do that, we're going to head over to GDB, and we're going to run that first fuzzer that we created, which is just a bunch of A's. And so you can see our stack is full of A's here. And what we're going to do is look at the stack a little bit more in depth, because we want to find the top of the stack. So we're going to go X over 100X, and we're going to give it the stack pointer there. And so we see a bunch of A's here, but we don't see the top. So let's go ahead and subtract, I don't know, 700. And okay, there's zeros here, and we can look down, and okay, so here's the top right here. So we want to select a row with all A's. Probably not this close to the top though, because GDB is weird with memory addresses, which can be a nightmare sometimes. So we'll pick a little further down. So we'll grab this one. And so we'll come in here, we'll paste this in, and now we're good to go. So now we can run this code, and we should be able to start up our reverse shell. Alright, so now that we have everything set up, it's time to get our reverse shell. So to do that, we're going to head back on over to our terminal here, and we're going to go ahead and run Python exploit, and we're going to put that in a file called shell.in. And then next, we're going to fire up Metasploit so that we can start our listener here. And I already started the database for Metasploit today. That's why I didn't run msfdb run or start it with Postgres first. So next I'm going to use the multi-handler, and I'm going to set my payload to Linux x64, and this is going to be our shell reverse TCP. And then I want to see the options, and I can see I need to set my lhost here. So I'm going to go ahead and say set lhost, and we're just going to use localhost, and then we're going to go ahead and run this. And so you can see I started my reverse TCP handler here, so I'm waiting for that connection from that shellcode. So then if we go over to GDB here and we run that shellcode, you can see we start the program. A new process is created with user bin dash, and dash is just a variant of bash. It's just a smaller version. And so we come back to our listener here, and we can see that there we have it. We have created a reverse shell right here. Session 1 has been opened. There you have it, boys. That's our shell. So if we look here, we can see all the files in here, exploit everything that we had created. Thanks, guys.